Okay, so I've only got till noon, so I'm going to hopefully not fly too fast. I also brought some silly putty. Um, it's more than Gareth brought, but that's okay. So I'll just leave it there and we can see what happened, what the rouse time or reptation time of that is. So I'm going to sort of, so what I'm going to tell you a little bit about stress and elasticity, because that's necessary to try to understand what's happening for the stress of polymers. Gareth's done a great job of telling you about rheology, so I'm just going to highlight a couple things, not much, that he said, and then go on to discuss the properties of unentangled polymers in the melt state, which is Rouse dynamics, and then unentangled polymers in solution, so-called Zim dynamics, and then hopefully get on to say something about entangled polymers, either in the melt state, which would be this state, or in solution. Okay, so first I want to say just a little bit about rubber, because that is a very simple way to understand the stress in polymers. So we've already seen nice experiments stretching this. So rubber is, of course, cross-linked polymers, and there are a certain number of monomers between the cross-links, and those monomers act as thermal springs, as we saw yesterday, and so they're flipping around, and you get some stress by stretching them. Okay. So the free energy per unit volume in stretching the chain, as we saw at the Gaussian level, is, well, each chain, we've got a certain number of chains per unit volume. Each chain is living in a harmonic well, which we derived on Monday, with where R is how far you've stretched it out, and the spring constant is given by the thermal energy, and also 1 over n, where this n is the number of monomers between the cross-links. Okay. So if I deform it, then I'm going to change R, the sort of average end-to-end distance, from some initial length, so I could call it nb squared, so the square of the average length squared that it starts with. I could stretch it in the x, the y, or the z direction by some amount. Okay. And then if I just define the ratios of the x over y and z relative, that should have been a y, to the initial length as lambda, my extension ratios in the different directions, and I have a nice simple compact expression for the free energy as a function of my stretch ratios. Okay. And so this is the simplest way to understand rubber elastic theory. This is the so-called neo-Hookean theory, which Gareth had shown trying to fit to the data points previously. Okay. If we want to be fancy about it, we could bundle things into some sort of a tensor W. But importantly, it depends on if I can write it in terms of the number of chains per unit volume, which is the number of monomers per unit volume divided by the number of monomers per chain. Okay. And then that is what controls the spring constant of it. Okay. And so if you stretch it, then what will happen is it'll stretch out in one direction, it may come back in the other direction, and the modulus that you get from stretching it, which Gareth talked about, is basically kBt times the monomer concentration divided by the number of monomers per crosslink. Okay. This will turn out to be basically the same thing describing silly putty, except now it's not monomers between crosslinks and silly putty, but between entanglements, which we wave our hands and say behave like crosslinks. Okay. Actually, this theory is meant, when I said before that if we stretch a single polymer out all the way, eventually we violate this harmonic approximation. Okay, and so there is a maximum stretch that you can get to, and that depends on how many monomers there are between your crosslinks. And that maximum stretch is actually square root of the number of crosslinks, okay, which is typically 2 to 10. Or even larger, depending on how stretchy you make your rubber, depending on how many monomers you can get between your entanglements. Pardon? You estimate that by saying the average end-to-end length to begin with is something like the square root of the number of monomers. The maximum length you can get is n, because you stretch them all out. So the ratio of the maximum n divided by the original length, which is the square root of n, that ratio is the square root of n. Yeah, good question. Everybody ask a question if you if you want answers. Okay. So let me say a little bit about stress. We can sort of more or less derive the same kind of thing without going to a free energy, although we use it to begin with. So the stress is the force per unit area. Okay, and if I put a little area somewhere, I can say, well, let's look at the strands that cross that area. Okay, so there's the force. Okay, and it's coming across this particular area. Okay, so the stress is actually related to the separation between the particular points and the force between those. And I can then end up writing that as the average of the end-to-end vector multiplied by the force. And because we have a Gaussian approximation, that force again just becomes the end-to-end vector with the factors of kBt from the spring constant. Okay, so we end up getting, if we just do the algebra, which I'm not going to do, we end up getting a stress which is related to the end-to-end distance squared divided by its initial end-to-end distance, where I've bundled together my monomer length times b squared to my average end-to-end distance to begin with, multiplied again by this kBt times c over n. So that's my modulus. Because this object plays the role of a strain, because it's telling you how the lengths have changed relative to how they originally changed. So I've got a modulus, a stress, which is a modulus multiplied by my strain. Okay. We can make it more fancy, and I'm not going to worry about that because we're not going to treat things at a higher level. We'll have these slides for those who want to do more sophisticated calculations. But the thing to take away is that the modulus of a polymer system is essentially kBt times the number of strands that are being stretched per unit volume. So this will be crucial when we try to understand the stress in the Zim model or in the Rouse model when things are changing in time. And so we can just say, how many strands are there per unit how many strands per unit volume? Give them a kBt. I could turn that into the number of monomers per unit volume and then divide it by n, which is the length of my strand. Okay, so we're going to use this repeatedly in trying to understand what happens in the Rouse and Zim cases. Okay. So I'm not going to talk about. I'll skip over this in the instances of time, but you can talk about the stress-strain relations for a piece of rubber. Here's an example of theory. An experiment doesn't fit the theory exactly, like is always the case. There are a number of reasons why the simple neo-Hookean theory, which we just talked about with lambda squared, doesn't work in extreme cases. If you stretch it beyond the Gaussian limit, that can cause problems because there's a maximum stretch. A real rubber, these are designed not to do that, but real rubbers can actually crystallize sometimes at large strain because you're aligning the chains, and then they lock up. The other thing that's quite interesting is that if you make your rubber soft enough, you've got many, many monomers between strands, you unavoidably get entanglements between the strands themselves. And so the modulus is governed by both the real crosslinks that are in there plus the entanglements. And so there's a contribution from both of those. And then the modulus of entanglements is a little bit different from the modulus of crosslinks. Because now, here, let me have someone hold that. Okay. And you can hold these. Okay. I've never actually tried this, but if we stretch it, you can see, this doesn't work because it doesn't slide. So you can get some slippage happening between the entanglement. But that doesn't happen at crosslinks. So because of that slippage, the initial modulus of a highly entangled rubber is a little bit softer than the neo-Hookean rubber. And then, so the presence of entanglements gives you a different kind of a softness of the rubber than the absence of entanglements. You can stop now. Thank you. So the simplest is a neo-Hookean, which is the one we all use because it's easy to do calculations with. If you stretch it too far, then you've got to use some little more sophisticated models. If you have entanglements, then you need even more sophisticated models, and there's one by Panyakov and Rubinstein, which is a really good one, because it takes into account the motion of the entanglements. The disadvantage of this model, despite doing a great job of handling that softness when you stretch it, either when you do a uniaxial expansion or when you do what Gareth called a biaxial compression, which I would call a uniaxial compression, but we can have an argument about that later on, is that this model only works for in the same limit of a Gaussian chain. So if you were to stretch it all the way out, this model still doesn't work correctly. So there's still ways to go in trying to understand rubber elastic theory. Okay. But what I wanted to mainly get across for understanding polymer dynamics is the concept of the stress being proportional to the number of chains per unit volume, the number of elastically active strands per unit volume. Okay, so now let's switch to dynamics. Okay, so Gareth has told us about rheology and rheometry. We have complex flows that we've looked at, and we've started to look at the different kinds of measurements that one can make. And hiding between these is constitutive equations, which tells us what we think is the physics going on behind the material deformation. How does stress relate to strain, and ideally, how does that encode the microscopic physics of the molecular degrees of freedom? So I want to take us along the way to try to understand that. Okay. Here is just some movies showing the different effects of shooting a drop. So here I'm just shooting a Newtonian fluid. This is a movie due to Oliver Harlan. And these are calculations of essentially, this is Newtonian, and then these three are polymer solutions with different molecular weights of polymers at different concentrations. And so depending on the concentration or the molecular weight, you either can get, it stretches out a bit longer and you get fewer of these, see the satellite droplets, you get fewer satellite drops. Here you get just one drop that then engulfs it, and eventually it becomes so stretchy and elastic that it actually can't, at the rate that they're injecting the droplet out, it can't butt it off. Okay, so that's all controlled by the high molecular weight polymer that's in there. Okay. So if you want to design something to send, say, chemicals over a field, and you don't want them to drift little tiny drops into the next field, then you want to design it this way. Okay. I'm not advocating putting chemicals on fields, but we do need to worry about that. Okay, so Gareth has shown us great demonstration of the Weissenberg effect due to first normal stress in polymers. There are other instabilities that can also occur due to the molecular features, in particular due to the normal stresses. And so this is the sort of a playground of nonlinear phenomena that we eventually try to understand at a molecular level. Okay, so I'm just going to remind you a little bit about what Gareth said at the very end. So viscoelasticity is where we say the stress has a modulus multiplied by a strain, and that modulus, as Maxwell told us, can have a time dependence which can fade away after you apply a strain. From this modulus, we can determine a viscosity, which is essentially, if I integrate the time dependence of that modulus over time, the integral of that is basically has units of a modulus times a time, which is a viscosity. Okay, so we can think of obtaining the modulus, the viscosity, by integrating the relaxation function if I have a method for calculating the relaxation function, or simply just estimate it, because if I had an exponential, of course, an exponential function is the nicest one that we have, and if you put an exponential in there, which has a relaxation time, then you'll get a modulus, a viscosity, which is some modulus times the time. Okay. He told you about oscillatory rheology, G prime and G double prime, so I don't need to go over that. At the very end, he introduced the Maxwell model. Okay. And the Maxwell model is indeed the simplest model. So the idea is that the modulus has got just a single exponential. Of course, we can do all the integrals for that, and you get a nice form. And the form has the properties that at low frequencies or low Deborah numbers, it behaves viscously because you're actually applying a frequency which has a time scale which is such that it doesn't perturb the internal time scale of the material. But at high frequencies, you're going faster than the relaxation time of the material. Behaves like an elastic solid in this case. So it crosses over from something which is viscous to elastic. Okay. And as Gareth showed at the end, this is not what happens in real materials. Okay, and in fact, you can use it as a fingerprint or a signature for different materials. So on the left is the Maxwell model. Okay, and I've shown 3 different kinds of polymers here. Once you've looked at these enough, you can sort of start looking at the bumps and saying, oh, that bump can mean something at a molecular level. So this is what one finds for very long entangled linear polymers. Okay, these are 2 different lengths. Down here, sort of looks like a Maxwell model. In here, the G prime is basically independent of frequency. Okay, so over here, it's behaving a lot like a rubber. Okay, so this is silly putty in the rubbery regime. But eventually, at high enough frequencies, you start seeing this turn up again. Okay, and if we think about frequency as being roughly analogous to length scale, so at low frequency, you're probing processes that happen at longer length scales. So down here, you're basically looking at low frequencies. You're just looking at it as a entire liquid in the rheometer. These intermediate frequencies, you might be looking at a length scale of order the size of the polymer, something like that. Actually, in the entangled polymers, what you're looking at is that you're starting to see the size of the polymer around here, and as you move in, you're getting smaller and smaller and smaller until you reach the distance between entanglements down here. And then now you're starting to wiggle the properties of an individual chain between entanglements. And so this is looking at the properties of an individual chain between entanglements. And so this turns out to be the Rouse behavior, which we're going to see in just a couple minutes. Okay. Star polymers have some weird stuff going on. It looks like a plateau, but then it comes down, and then it comes back up again. So a star has got these arms that actually take a long time to pull back. Okay, and so that the presence of the arms pulling back and the fact that they take a long time for the arm to retract to be able to go out someplace else in the star polymer leads to this plateau, and eventually the arm does retract, and then it comes down, and then it comes back up again. Okay, so that's very strange behavior of stars. These are comb polymers, which have a bunch of little bumps related to the individual arms moving along. And if you start putting arms at different controlled numbers of arms and lengths of arms, you can change these features. Okay. So a critical test of a constitutive model is whether you can predict the different kinds of relaxation dynamics or elasticity that are associated with G prime and G double prime in here. So just take down here. So this is G double prime. It goes up and then it comes down, meaning there's some relaxation mode here, and then it comes up, and then it starts to come down again. There's another relaxation mode over here, and then it comes back up. So this first mode would be one of the arms of the comb coming out, and then over here is where the whole chain finally lets go, and the entire comb can start to relax. Okay, so we can sort of unfold. Actually, no, this is the entire. Actually, I'm not sure which, so I'm not going to speculate. Okay, so let's look at single polymers first to try to understand what's happening up in this regime up here, which is high frequency, which is actually when we're looking at the dynamics between the entanglements of just a single chain moving. Okay, so that'll be the Rouse spectrum. Okay. Okay. So for the Rouse model, I am going to treat it. We treat it beads and springs, which is what Gareth threatened I would tell you about. Okay, so we treat a polymer as beads connected by Gaussian springs. And so the energy function, so I can write down a partition function which we wrote down before, but we can just focus on the energy function, which is essentially a sum of springs. Okay, so I have a spring constant for each spring, and then I have the separation between springs. Okay. Now what I've got is I've said that every Kuhn step is like a little spring. Okay. Remember what I said before, we could also write just a giant spring for the entire end-to-end distance. Okay. And I did successfully unentangle my polymer from yesterday. Okay. So if I wanted, please don't tangle, I could treat the dynamics of just the ends with just the ends. But that doesn't give me all the internal information about these modes. And you can see that as I shake it around, there's an inhomogeneity of the way things are happening. There are things happening on the inside that are not captured by the end. So the equivalent way is just to write it in terms of individual modes. And I'm going to go all the way down to the single bead level and assume that each bead is a spring. And that way I can get all the internal dynamics, or as much as possible, in there. I'm going to hang that up. Well, maybe not. Because if it gets close to itself, it entangles. Okay. So, what's the equation of motion? The equation of motion would be, should be F equals ma. So I'm going to have ma over here, but I'm going to assume that everything is so viscous that I don't need to worry about my inertial forces. Okay. And so the inertial forces have died away very quickly. So this is effectively low Reynolds number flows. I've got a drag force, which tells me, well, if the monomer position changes in time, there's a drag that pulls it back. And there's a restoring force due to changing the energy function. So just take a derivative of my energy with respect to my position. And if I want to get fancy, I can add Brownian noise, which kicks it around and has a temperature and a drag, and this noise is related to the drag by the fluctuation dissipation theorem. Okay. So this would be the way to sort of say, here's the equation of motion. When I put that energy function in, I get a very simple equation, which just couples each spring to what's happening on the springs on the outside. So that's a very simple equation, which Rouse wrote down. So there it is again. It has a spring constant, which is set by my thermal energy. Okay. And I could, this actually turns out to be a discrete version of a second derivative. I can make a continuum version of this. I put the drag on the other side, so I can make a continuum version, which is d squared dn squared. And now we can see actually this is a diffusion equation. So it's dr dt is minus k times the second derivative with respect to an arc length. This n is the arc length along the chain, so it's a diffusion equation. Okay. So we've all done separation of variables. So that's what Rouse said. Let's assume that my position as a function of where I am along, so n is the monomer position, r is my position in three-dimensional space, and I'm going to just expand that in cosine modes. I don't include any sine modes because the cosine modes have a zero tangent at the end, which corresponds to a free end condition. There's no force on it if you've got a zero tangent at the end. So that's why I get cosine modes. Then I go through, and once you've gone through that, you get a super simple equation. So what this does is it turns this derivative into, each time you take a d by dn, you've actually pulled out a p, and so you get a Rouse modes whose spectrum depends on the mode number, and then plus some noise. Okay. So I've just taken this expansion, thrown it up into here, turned the derivatives, and that's what I get. So now it's a very simple equation. Okay. And each mode depends on a fundamental mode, I'll call it tau 1, but then scaled by p, which is the index which comes down here. So I've written it as 1 over tau p. That means that there's a p squared up top. Okay. So here's an example of just solving an initial condition. So I started with a set of Rouse modes, which was very wiggly, which was the red one, and let it go. And what you find is very rapidly, the red one has gone away, the ripples have gone away, and you get something that's very smooth. And in fact, at the latest time, I get something which is just the purple one, which is then slowly relaxing. And if you look at this purple one, it's very close to a half of a cosine mode. Okay, so what's happened is all the other modes have gone away quickly, and they've gone away quickly because their time scale goes as 1 over p squared, the mode number. Okay, so, and because that's in an exponential, that rapidly goes away. Okay, so there's a rapid decay for the higher order modes, and the final relaxation is basically determined by this lowest mode. Okay, so that lowest mode, tau 1, you can see it scales as n squared. Okay, and I can bundle all of this other stuff. There's a drag, there's a KBT. You can bundle all that other stuff into a monomer time. So this would be the time scale if I just had a single monomer. Okay, so this is what we call the Rouse time. Okay, so it's the time for the entire chain to sort of relax. The small scale modes don't matter so much. Okay, and it's mainly dominated by this fundamental mode. Interesting to note, this is going to be super important, that the Rouse time is not linearly proportional to the monomer time with a factor of n, but it goes as n squared. Okay. You might have thought, well, if I've got twice as many monomers, it should be twice as long. In fact, it's 4 times as long. And that is because it's a diffusion equation. We're going to see another way to think about that in just a second. Okay. Okay. So now let's think about it a different way. So I'm not going to use Fourier expansions anymore. Okay. Let's think about what's actually happening with my polymer in terms of monomer diffusion. Okay. So let me just hold it up. So if a monomer is trying to diffuse, KBT is kicking it around, it's trying to diffuse. It's got to carry some friends with it. Okay, so the diffusion of a single monomer just doesn't happen because of the connectivity. So they've all got to sort of move cooperatively together. Okay, so rather than the diffusion time scale being determined by the number of monomers, it is determined by the monomers, but the farther you go, the more monomers you implicate, and you have to pull along. And so it gets slower and slower. And that's ultimately the source of this n squared behavior. Okay. So we focus here, we say I've got some small number of monomers, and let's imagine I do a step strain. And I could say I stretch them out, and then I got these little groups of monomers that are all trying to relax back. So I've got my solution, I've done a step strain, all my polymers have pulled out, and now they're all trying to relax back. So I'm going to focus on a little blob that sort of relaxed back. If I just had n monomers that were not connected, I would expect the diffusion coefficient, so the diffusion coefficient is kT divided by the drag, that's the Einstein relation. So, and the drag goes as 6 pi eta times the size of my object. And if I've got n of these monomers, they're all going to be dragging along. So my diffusion constant would be the monomer diffusion divided by the number of monomers in my blob. Okay. However, those are conspiring to live in a region of space which goes as r squared. The scales as n, that is n squared. And so if I want a relation between how the monomers diffusion time and their monomer number and space, I need to take these into account. So the time scale for things to relax for these number of monomers would be related to the length scale over which they're relaxing. That's my typical size of my monomer region, divided by the diffusion coefficient related to these monomers moving around. The diffusion coefficient picks up a factor of n because that's the monomer diffusion divided by n. R squared is proportional to n. So that means the time scale for things to relax within that region within which they're confined scales as n squared. So this is the same thing that we got from doing the Rouse modes. Okay. So again, if n is the entire chain, of course, this is just n squared times the monomer time, which is what we had before. But now let's turn this around to try to ask about what's happening for the time scale of these different regions. So if I look at, if I take these together, and I turn it around, and I say, well, I've stretched it, and I want to say, what's the size of regions that have relaxed after a certain amount of time? So just take the square root of this. I'm going to get the size of the relaxed regions scales as time over the monomer time to the 1/2. Okay, so you stretch it out, and I want to go ask, after some amount of time, what's the size of regions that have relaxed? And the size of that region scales as t over the monomer time. Okay. I can also ask about how things are moving in space. Okay. So if I take this n of t and put it back into the relation between, say, the time scale and the position. So let me just do it down here. So time is length squared over the diffusion coefficient. The diffusion coefficient is a monomer diffusion divided by n. Okay. N scales as r squared. So I'm now using the behavior of the Gaussian chain. And so now I get a relation between r to the 4th and my time scale. Okay. Turn that around, and that says that r goes as t to the 1/4. Okay. So what is that telling me? That's telling me that after a certain amount of time, the distance that it can explore, that is the size of this region, scales as t to the 1/4. So it's slower than diffusive. It's subdiffusive by another factor of a square root. Okay. Okay. So the idea, you stretch the chain, and then things start to crinkle up, and the sizes of the regions that are crinkling up are getting larger and larger. They're having to cooperate with their neighbors to do that, and because of that cooperation, the diffusion is slow and it's subdiffusive. Okay. So that gives us this scaling of r going into t to the 1/4. Okay. What about the stress? Okay. So the entire chain, the stress of the entire chain should relax on the Rouse time. Okay. So if I were to measure the modulus of the material after stretching it on the time scale at which the material has relaxed entirely, it should be the number of chains per unit volume. I've got one chain, basically. So it's number of monomers divided by the length of the chain. Number of monomers per unit volume divided by the length of the chain. Okay. And then I can do my estimate of the viscosity as being modulus times the time scale. So I've got a 1/n. My time scale goes as n squared. That's my Rouse time, which says my viscosity should scale then as the size of the chain. Okay. Now, what about earlier times? At earlier times, I can say, well, at earlier times, I want to look at how many unrelaxed chains I have per unit volume. So I started out with it fully stretched, and after the Rouse time, the chain has come all the way down. Okay. But after a shorter time, it's relaxed a little bit, and I have subchains that have relaxed, and the number of subchains that have relaxed is much larger than the total number of the total length of the chain. And so G of t is now basically kBt times the monomer concentration divided by the length of the subchains that have been able to relax the stress. So now I take my modulus, and my modulus now has a numerator, which is the number of unrelaxed strain, of the number of relaxed segments. Okay. And if I put the n of t that I had in before, I get a modulus that scales as t to the minus a half. Okay. The modulus at early times is actually set by 1 over n naught, which is how far I've stretched it out. Okay. If I've stretched it out so far that I go all the way to the every monomer is unrelaxed, then my modulus is as high as it can be. Okay. So this gives a power law relaxation of the modulus, rather than the exponential that we were talking about as the simplest case. So let's think about what that implies for both the monomer diffusion and the stress relaxation. So in terms of monomer diffusion, so I'm going to plot the monomer position on a log-log plot. There's a time scale which is the Rouse time. Beyond the Rouse time, I should have Fickian center of mass diffusion, because beyond that time the polymer is just orienting as a single object and diffusing along. For smaller times than the Rouse time, if I just tag a monomer, that monomer is moving around, but it's constrained by its neighbors, so it moves subdiffusively. So if you tag a single monomer, it moves subdiffusively until it's moved about as far as the length of the chain, which means that the whole chain is now oriented itself, and that's the Rouse time. So you get subdiffusive with a power law of a quarter, and then ordinary Fickian diffusion at that point. The stress has a similar signal. At time scales smaller than the Rouse time, so I'm plotting the log of the modulus versus the log of time. The modulus comes down with a power law of -1/2, which comes from this Rouse spectrum. Once you get to the Rouse time, then it decays with an exponential. So on a log-log plot, an exponential decay looks like that. So you get power law, which then eventually crashes down by an exponential. Okay. And so if you're in this regime, you'll see this power law. Okay. And so you can derive all of this quantitatively from the Rouse modes. That's all in Doy Edwards' book. This is sort of a hand-waving way to get the same information. Okay. Now what about chains in solution? Because what I've told you about here is Rouse chains, which have basically assumed that I have a Gaussian and behavior, that my Flory exponent was 1/2. If I'm in solutions, two things happen. One is I need to worry about this Flory exponent being something other from 1/2. So it'll be 1/2 if I'm in a theta solvent, as we talked about on Monday or Tuesday. It'll be 3/5 if I'm in a good solvent, and it might be something else if I'm somewhere in between. Okay. You also have to worry about hydrodynamics. So my polymer is in flow, not in flow, in a solvent. If I move the polymer along, I can think of it moving such that the fluid goes through the polymer. That would be so-called free draining, where every monomer is experiencing the drag. Okay? If I think about every monomer, that would mean that there's a lot of drag. The alternative is that it moves as a rigid sphere. There's fluid contained inside that's not moving relative to the polymer, and the only drag is between the sort of the sphere of influence of the polymer and the solvent around it. Okay? And that's the so-called Zim approximation. Okay? So we assume that there's no flow happening on the inside, so we don't have free draining situation, but we have flow going on the outside, and it moves more or less like a colloid. Okay. So in that case, if we think about the drag constant now goes as the size of my sphere, and the size of my sphere then depends on the monomer number with some exponent. Okay. So the diffusion coefficient then is the same. The diffusion coefficient goes as 1 over a drag. So the diffusion coefficient would be the diffusion coefficient of a monomer times 1 over r. Okay, because it gets smaller. If it was a monomer, my r would just be a monomer size. Okay, so the drag constant is smaller by r, but that r, remember what we had before, if that was a 1 over n for the Rouse case, now it's going to be 1 over n to some power, either 3/5 or 1/2 in the Zim case. And then we can just put that into the same arguments before, and you're going to see we're going to get different power laws. Okay. And so we should contrast this with the Rouse case. Okay. So we can do exactly the same sort of argument we went through before. But when it comes to R, we now use the Flory exponent. And when it comes to the diffusion coefficient, we relate it to the monomer diffusion, not by the number of monomers, but by R. Okay. And then we can go through the same type of argument we got before. We find that the time scale for relaxation of a region of size n goes as actually n to the 3 nu, where nu is the Flory exponent. Okay. And if we relax for the whole chain, of course, we can let that be capital N. Okay. So now we have right. Okay. This says melt, but I'll change that in a second. So this is the relation 3 nu. Now we actually have a different nu depending on which solvent we have. So if we have a theta solvent, nu is equal to a half, so we get n to the 3/2. So this should be theta solvent, not melt. And if we have a good solvent where the exponent is 3/5, then we get this factor of 9/5, which would be the good solvent. You remember for the Rouse case, we had n squared. So both of these are smaller than n squared. And so what the Zim model does, it actually moves faster. Okay. So rather than scaling as power of n squared, it scales as a smaller power. So the relaxation dynamics of the Zim is faster in terms of numbers of monomers. Okay. We could go through the same argument to find that the number of groups that have relaxin times t goes as t to an exponent which is 1/3 nu. And that R, this sort of anomalous diffusion that we found before was a quarter, now is a third. Interestingly, there's no Flory exponent there, which is curious. Okay. And so we'd have the same type of behavior as before. And so you'd find that now that you get subdiffusive behavior up to the Rouse time, but now with an exponent of a third. And then after the Rouse time, you get Fickian diffusion. Similarly, we'll do the modulus in just a second. Okay. So if we just compare those two, here's the relaxation time for the Rouse chain, which scales as n squared. And here's the Zim time, which scales with an exponent depending on our conditions. The number of unrelaxed chains, or relaxed chains in the Zim case goes as this 1/t to the 3 nu. If we do the same argument of finding the modulus, so the modulus of the viscosity and the modulus. The viscosity is the modulus times the time scale. So this would be the linear viscosity where I allow the chain to relax entirely. If I put in the Zim time, that actually scales not as n, which is what I get for the Rouse case, but n to some power. Okay. And that power that involves the Flory exponent. Okay. So what one typically does is you measure the viscosity as a function of molecular weight, and then you should have one of these two behaviors depending on what you think your solvent quality is. If it's not that, that means there may be something else going on. It might be charged, you get polyelectrolyte effects, or something else going on. Okay. You can also work out the modulus in the same way that we worked out the modulus before. It scales with a different power law, as you might imagine, and the power law depends on the nature of the solvent. Okay. Okay. So both the Rouse and the Zim models have this behavior of a relaxation as a power law, okay, and then that power law turns into an exponential. Okay. With some exponent, so in the Rouse case, it's an exponent of a half. In the Zim case, it's 1/3 nu. What I didn't derive, but I'm just going to tell you, is if I have a semi-flexible chain, so that I actually have, so it's like this one, you can now look at essentially the vibrations of my string, and if I look at the dynamics of the vibration of the string in solution, you find you get an exponent of 3/4. So that will be for a semi-flexible chain in solution. Okay. So one way to tell what kind of change you have is to look at what's going on here. Sometimes you don't actually have the ability to look at it in the time domain. It's easier to look at it in the frequency domain. You just get your rheometer and you move it at high frequencies. If I put this power law into the Fourier expansion, okay, when you do a Fourier expansion, it roughly turns time into frequency. What you find is that g of omega goes as omega to the plus m, where m was the same power law that was governing the time decay. Okay. So what you can do, so this is an example from, actually Ralph Colby had a couple papers demonstrating, a paper demonstrating this quite nicely. On the left, I'm showing unentangled polystyrene melts. And this is the spectrum. Down at low frequencies, you've got G double prime is here, and then G prime is over here, so it's liquid-like. And then at high frequencies, they cross over, and they're both G prime and G double prime go with the same power law, and the power law is a half, which corresponds to an exponent of nu is equal to a half. This is dilute polystyrene solutions. Okay, same thing as melts, but solutions. They have the same type of behavior. Interestingly, and the power laws for G prime and G double prime are the same. I mean, they're same as each other. The values are different from the value over here. Okay, that's because you put nu is equal to half in here, and you get an exponent of 2/3 rather than a half. The other thing that turns out when you actually calculate G prime and G double prime is that the shift between these vertically also depends on the exponent. Okay, so that's a feature that one can look at. Okay, so all the internal modes that one sees are revealing themselves in these high frequencies. And you can think of it as what we're doing as we go higher in frequency, we're looking at larger, faster and faster vibrations along the backbone. Okay. Not one nice application of this, which I'll just say a little bit about, is a coil stretch transition in polymers. So if I take a very, very high molecular weight polymer, this one's going to be entangled now. Oh, not so bad. So in solution, it's basically described by the Zim model. Okay, so the drag on it is just on the outside of the polymer. Okay, so this is an example of so Dejean explained that as we change the magnitude of the flow, we can go from something which is I think this is roughly the end-to-end distance of the chain. At low flow, it's not very well deformed, and then at high flow, if one has a certain amount of, if it's an extensional flow, you can snap it out, and it undergoes a coil stretch transition from here to here. One way to think about that is that as you stretch it out, you're sort of removing the internal fluid that was being carried around in the Zim approximation. So, here it is here. You go from the Zim of a coil, where the drag force goes as the molecular weight to the nu, turns out, the Flory exponent, to the Rouse relaxation of a rod that's been stretched out. And that scales as a different power molecular weight. And if we compare these to each other, you find a ratio of forces such that, in fact, it's a much greater force on the coil than on the chain. So that pulls it out. Okay. So just say a word about concentrated polymers. We talked before about the fact that when you go from dilute to semi-dilute to the melt, the exponent goes from the Flory exponent of 3/5 down here. In the melt case, it goes as n to the 1/2, the ideal case like the theta solvent. Okay. Not only does the structure make a change here, but the hydrodynamic interactions, or the effect of the solvent flow, is such that you go from the Zim case, where as the polymer moves, it's got to shuffle solvent around inside, and the way the relaxation dynamics is actually governed by having to deal with the hydrodynamics. As you get more and more polymer in there, the polymer acts to effectively screen the hydrodynamic interactions amongst the monomers. And eventually that hydrodynamic screening length gets to be smaller and smaller and smaller, similar to when we talked about how the blob size gets smaller and smaller and smaller. And those cross over at more or less a similar type of point, so that at a high enough concentration, it'll be described by Rouse dynamics rather than Zim dynamics. And that's why in the melt case, there is no screening and it behaves perfectly like a Rouse dynamics. Yes?
Is this somehow related to when you inflate the plastic balloon at the beginning, it's really hard, and then you undergo some kind of phase transition when it's easier to...
That's a little bit different. That's related to how the area is changing as you inflate the balloon, and it's related to the stress in there. So it's that one's a geometric transition. Yeah, yeah. Now what's happening in here is you get more and more polymer, so less and less solvent. Okay, and then so the contrast between the solvent and the polymer has gone away, and then you actually there's nothing left to think about in terms of the solvent. Okay. Okay. So I have just a little bit amount of time, so I want to say a little bit about entangled polymers, because if we make it large enough molecular weight, high concentration, then they start to entangle with each other. Okay. So the theoretical understanding was from these three gentlemen, Pierre-Gilles Dejean, Sam Edwards, and Marcel Doy. Okay. And so the left would be a sort of a realistic, quasi-realistic set of spaghetti, where I've got a red one and blue ones. And what Dejean suggested and then Edwards put in and Doy put into action was to think of all the blue chains that are surrounding the red chain. I'm going to just fold those into an effective tube that constrains the red chain. So rather than solving a really complicated dynamical problem of every chain, I'm just going to solve one chain by a tube. Okay. And now I'm going to say, well, how does this chain move in the tube? Okay. And the relaxation, the very, very long relaxation in the silly putty is related to how long it takes this to get out of the tube. Okay. Okay. So there's some molecular weight or some number of monomers per chain where they become entangled. That's called the entanglement molecular weight. Or typically, so there's distance between entanglements, which we call the entanglement molecular weight. Typically, it's got to be at least 2 or 3 entanglement lengths long to be able to be fully entangled. Okay. The idea is transverse motion is not allowed, but you can just move along your chain. There is a length scale, which is the so-called entanglement length, which is some number of monomers. And so the tube diameter is the square root of the number of monomers between entanglements. There's no theory for this value. It's actually a property of the chemistry of the polymers. Okay, so if you just have a particular polymer, depending on how bulky the polymer is, how flexible it is, there will be a tube diameter. There have been a lot of attempts to come up with theories, but that's at the moment that's just something we have to take for granted. It's typically 10 to 20 Kuhn steps. So remember I said if you're about 15 Kuhn steps beyond or longer, the random walk becomes a Gaussian chain. So we're going to describe everything as a Gaussian chain. Okay. And there's a tube length, which is we could think of as some number of tube steps, and that number of tube steps is actually that we call that the number of entanglements. So we can think of it that there's entanglements sort of coming through every so often. So I take my tube diameter and just sort of move it along, and that's roughly the number of entanglements. Okay. So the way things relax is by essentially diffusing along the tube. Okay. So I've got a length of a tube, which I can write in terms of either the number of monomers. Well, this is the number of entanglements multiplied by my tube step. I've got a diffusion constant, similar to what we had before, which is essentially a monomer diffusion divided by the number of monomers. Okay, so my relaxation time is the time to diffuse along the tube. So the length squared of the tube divided by my diffusion constant. The length goes as n, so length squared goes as n squared. My diffusion constant goes as 1 over n, so that gives me an n cubed. So that means that my time scale to relax out of the tube scales as n cubed, or the third power of the entanglements. Okay. So that's a very, very long time. I could also write that, have I written it here? I can write it, I've written it here as tau e times z cubed. Tau e is the Rouse time of an entanglement strand. So if I go down to an entanglement and I say, what's the time scale for that to wiggle around? It has a Rouse time. And that Rouse time, which scales as the square of the number of monomers between strands, is setting the time scale for everything. And so I get the time scale for reptation by taking z cubed multiplied by that. Okay. What are the consequences of that? So if I do a step strain, actually the relaxation modulus, it can come down quite quickly. That first relaxation is because if I do a real step strain, I actually stretch it in the tube. So the tube gets a bit longer. That tube has to come down back to its relaxed length. And this time scale occurs on the Rouse time of the tube. Okay, on the Rouse time of the tube, the Rouse time of the polymer in the tube, it has relaxed back to the tube length. Okay, so this is the Rouse time of the polymer. Then it takes a long time for the polymer to wiggle out of its tube. Once I've gone long enough, which is essentially this thing I call tau d. D stands for disengagement, by the way. I didn't say that, sorry. Or the reptation time. Once I've gone that long time, then I get an exponential relaxation. But I have a plateau where it sort of hangs there for a long time, and that's when it behaves like a rubber. So I do a step, the strain relaxes a little bit, and then it just hangs there for a long time until then it eventually gradually relaxes. Yes? Yep. This thing here? Yeah.
Does that mean that if you have shorter entangled strands, you'll have a lot lower Rouse time, so that the...
Yeah.
Okay,
Yeah.
So
Yeah.
never mind.
Yeah. So, pardon?
So the more entanglements means much slower dynamics.
Yeah, more entanglements means slower dynamics. But if you have, say, polyethylene compared to polymethyl methacrylate, same number of entanglements, polymethyl methacrylate has a really bulky thing going on, so it has a larger tau e. So it'll have a larger, for the same number of entanglements, it'll have a larger relaxation time. So if you keep the entanglements the same, the time scale does change depending on the chemistry, because the chemistry determines tau e, determines Ne, and it determines the drag. So, yeah. I've got to stop in 30 seconds. Okay. What happened? Okay, so the relaxation spectrum, this is in time domain. In the frequency domain, the frequency spectrum is that the G prime, which is this one, comes up. Low frequencies, it's relaxed. Then you have a broad spectrum of frequencies where you have this plateau, which corresponds to this plateau. And then eventually you go to high frequencies. Now you're exploring the internal Rouse modes of the entanglement strand. G double prime, dominating at low frequencies because down here it's relaxed and it's a liquid. Then it looks sort of Maxwell-like, and this Maxwell-like corresponds to the relaxation, the reptation time that goes as z cubed. And then it comes down, and it's not very Maxwell-like, as Gareth was emphasizing, because it's got a whole bunch of modes inside of it. There's a bunch of modes that are not just the Rouse time of the length of the tube, but all the fluctuations within the tube, which go from the length of the tube all the way down to the entanglement strand. Once you get to the entanglement strand, you've lost the fact that it's actually either a melt or a rubber, and you just go back to the dynamics of the single strand. Okay. And that's about as far as I've get. So this is the sort of typical measurements of viscosity as a function of molecular weight. And for different polymers, you get something which is linear at some point, and then it crosses over to something which is actually 3.4. So I showed that it should be m cubed, but it's actually 3.4. There is a theory for that, so we understand that. It turns out that 3.4 is an asymptote on the way to 3. Eventually, it does cross over. So I think I need to stop. Is that right? Okay. I'll just leave that up to show that diffusion is even more anomalous for monomers in the polymer, in the entangled melt. You get one power law when you're below the entanglement strand. You get an even slower power law at the length scale within the length of the tube. Then eventually the tube is sort of Rouse-like, and then finally you get Fickian diffusion. So there's these 4 different regimes of monomer diffusion which are happening in there. So I'm going to stop, and we can eat.